Hello everyone, welcome back to my stream. I'm Alex, and today we're gonna continue following the Vulkan tutorial in Rust. And last time we implemented descriptor layouts and buffers and descriptor pools and set. We managed to create a uniform buffer in our Rust program, so we can transfer some data from the CPU to the GPU. But we were passing identity matrices because we don't have any code yet for creating transformation matrices. We are not using any library so far. So the goal for today is to implement basic matrix functionality so that we can add maybe rotations or translations. And in the Vulkan tutorial, they mentioned this resource which explains transformation matrices. It's from OpenGL, but should be useful also for us. So I will be going through this and then running our program, which is here. As you can see right now, we have just a plain rectangle. It doesn't apply any rotation. And the plan is to have this rectangle rotating. So let's see how we can do that. If I go to the code in here, you can see that we added this matrix for type, which is just an array of 16 floating point elements. And so far we implemented the identity method, which just returns a matrix with the identity matrix. So I'm guessing we will be implementing here new methods for like translate and rotate maybe. And this will need to take parameters specifying how do we want to rotate or translate. But yeah, that's the idea. And then we are using here when we render the frame. Here we are in the main loop of our program, and after we process events from the window and so on, we get an image from the swap chain and we proceed to render into it. Here, this section takes care of updating the uniforms. And yeah, like I was saying, we have this uniform buffer object with projection view and model matrix. But for now, we are using the identity matrix on all of them. So here on the tutorial, if I remember correctly, they were using if I can find it. Yeah, so our goal is to have the cube rotating. Where do we set the rotation? Trying to find this part of the code. Maybe it's on the previous chapter. Yeah, it's in here. So they are using this GLM rotate, which takes matrix 4 with all ones, Takes an existing transformation, rotation angle, and rotation axis as parameters. The first one returns an identity matrix, and for the angle, we pass in GLM radians multiplied by time. In the view transformation, we add a lookat transformation. Which takes the eye position, center position, and up axis. And for the projection, they use a perspective transformation using an angle of 45 degrees and the aspect ratio of the swaption extent. Let's try to go through this. So first, probably we want to introduce matrix multiplication. And in fact, I'm gonna start by moving this matrix code into its own module. And using it in here. Well, we're already using everything from Icarus. So I can go to our lib and add a new module, maybe call it math, and then use everything from it. Now we can add a new Rust source file and paste in this. And I will need to make these functions public. Let's make sure that we are still able to compile this. Looks like we do. Good. So now I want to maybe add some unit tests. So we can do that by creating a new module inside of this module, configuration test, node tests. And in here we can have functions marked as with the test attribute. Identity. I don't think we need to test the identity. But the next thing, maybe multiplication. And we will add a test in here. I'm thinking that maybe we can add a constructor. Well, probably so new or yeah, new. New is gonna take new is gonna take an array of 16 floating point numbers, and it's just gonna assign those and return self with E. So that way we can keep this member private, but have a constructor to create a matrix. So now we should be able to create matrix 1, which is mat for new, passing in an array. And what are we gonna pass here? Do they provide any example in here? First, they talk about matrix vector multiplication. I'm gonna just add increasing numbers. 1, 2, 3, 4 for the first row. Then 5, 6, 7, 8, 9, 10. Something like this for the first matrix. Then I want also to have a vector 4 type, right? Or vector 3. Let's start with vector 4 first. And in fact, I think we can use a tuple struct. Can we change this also to a tuple struct? That way we don't need to name the E variable. You can just do self like this, and this one. Oops. Something like this. Let's double check that we're still able to compile, and we are. So now I'm gonna add an implementation also for vector 4. Fn new. Takes also an array. We could arguably pass in just 4 floats instead of an array, but just for consistency, to have the same as for the matrix, I think this should be fine. Now we want to sort of multiply the matrix and the vector. Let me add in here. Let V is equal to vec4 mu. What are we gonna have here? maybe 1, 2, 3, 4. Maybe it's too simplistic of an example, but I think that's okay. Now we need to here import everything from the parent module, otherwise it doesn't compile. Yeah, now we just get some warnings about unused variables. And we can run our tests, cargo test, and check that they are running. We have a few. Do we have more tests? No, we just have one in here, and we can add assert false. It should make this test pass fail, sorry, and we have a failing test. So we can use a little bit of test-driven development. Let's see. So we want to implement multiplication. I think there's a way in Rust to Rust into ops move. Basically, we have a trait for operations that we can implement. Yeah, let's see. The multiplication operator asterisk. Right hand side is self by default, but this is not mandatory. So by default, when we implement mul, we implement multiplication for one type multiplied by the same type as the right hand side, but we can have the right hand side be a different type, which is our case. We want to have self to be matrix 4 and right hand side to be vec 4, right? So we can use this trait at the top of the file. Use it in here, and then we can, after the constructors, we can add an implementation for this. So impl mul for mat4, and do we specify the I think we need to specify the right hand side operator in here. So this should be vec 4, and then we add the mul function, which takes self and right hand side. Do I need to name it like this? Here they are implementing mul for the same type. Ah no, it's the syntax is like this. So self in this case would be vector and scalar is the right hand side. So we need that's the syntax that we want. Let me grab it. So we want to implement mul with a right hand side of vec 4 for our mat4 type. The output of multiplying a matrix 4 by a vector is a matrix, I think. Yeah, that would be the, no, it's a vector. Yeah, that's right. So the output should not be matrix 4, but vec 4. Right hand side is gonna be back 4. And here is where we need to implement matrix vector multiplication. So I'm gonna do it the dumbest possible way for now, and we'll see later if we can improve it. So basically, let's see. We want to multiply the first row by the vector, the second row by the vector, the third row by the vector, and the fourth row by the vector. I can barely see this. Yeah, this image is so pixelated. I can barely see it. Let's see. So we have self dot 0. This is gonna be ugly as hell. This is gonna be ugly as hell. The first element of the matrix, which is the first element of the first row, times the vector's first element. Wait a second, I'm gonna do some change to be more sane. And the vector 4, I'm gonna replace it by a real structure, which is gonna be x, y, z. This is gonna be way easier, and w. And then the constructor, I also don't care about having x, y, z, w, and self. Oops. Self x, y, y, z, w. And we need to change our test to take that into account. We just need to get rid of these square brackets. That should work. For the matrix, we'll keep it as a as an array for now. And I'm gonna add a comment here. Matrices mat4 stores its elements as, is it called row measure? Row measure? I think it is. So basically the first elements of the array are gonna be the first row, not the first column, because we could choose to implement it the other way, right? In fact, I think OpenGL does it in column measure order, so we need to be careful about that. Now we want to multiply first matrix element times the vector first plus self first element times y plus self dot 2 times left-hand side z times self dot 0 3 times right-hand side w. That would be our x it's very similar for Z. The only difference is that we need to take different row elements. So the actual formula is gonna be, this is gonna be 0 times, so this is gonna be the row times the amount of rows plus 0, right? This is gonna be 0 times 4 plus 1. This is gonna be 0 times 4 plus 2. And this is gonna be 0 times 4 plus 3. We multiply by 4 because there are 4 elements for each row. So in order to move from one row to the other, we need to have 4 elements. And then this can be the same, except that now we multiply this by 1. So this is the index of the row we're currently looking at, right? So let me copy that now. X, Y, Z, W, get rid of those. Y, Z, and W. And this one should be 1 for all of them. I'm gonna hard code it for now. But you can imagine that you can write this on a loop, no? This is 2, this is 3, this is 2, 3, 2, 3, and 2, 3, and then we can add here X, Y, Z, and W. Expected stroke math, right, this needs to be back 4. So self. Like it better like this. What if I name it back 4 directly? It still puts it in multiple lines. So now let's check an example that we know will work. Let's go with a simple example first, and is the identity. Identity, not identify. If we now do n times b, we can assert equals n times v should be v, right? And if we run the test, Vector 4 cannot be formatted using, so we need to implement debug trait for these types. Debug and probably also partial equals to be able to compare them. Derive debug, partial eq. We run it now. Value borrowed after move. So when we do the multiplication trait takes its I name this also sub output. So this takes its value by value. I think the simplest solution to this is to implement copy, clone and copy for this type. It is a relatively small type, just 16 bytes, so it makes sense to make it copy. For matrix, I'm not so sure. It is more heavyweight, but for vector, we definitely can make it copy. That way, when here we use it for the multiplication, since it's copy, it will copy instead of moving. So I think that should fix it. And we got a green test. Cool. So now we can look at a more complex multiplication example to make sure we're doing everything right. And after that, we can move on to translation matrices. So if we add in this one and use the same v, then what should be the result? M times v should be equal to a vector 4, which would have, I'm gonna put in here 1 times 1 plus 2 times 2 plus 3 times 3 plus 4 times 4. This is gonna be the first component, the x component. Then we have, well, let me do this in Python quickly. So 1 times 1 plus 2 times 2 plus 3 times 3 plus 4 times 4. This is 30. Then the second one is gonna be the second row of the the second row is 5, 6, 7, 8 times 1, 2, 3. So 5 times 1, 6 times 2, 7 times 3, 8 times 4. This is 70. The next row is gonna be 9 times 1 plus 10 times 2, 11, and 12, 110. Hopefully we don't run into precision issues. 13, 14, 15, 16, 150. And add the dot zero to make them floating points. Let's see if this still works. Looks like it does. So I think we have implemented multiplication right. I mean, this was the most simple. In fact, now that we have a test passing, let's try to improve this. So if we had a for I in 0 or for row in 0 to 4, we could have v dot v at row index is gonna be this thing. Where these zeros become row, 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 and row. Now we just need to define this v, which is just gonna be an array of 4 floating points numbers, and we can get rid of all this repetition and add self.output new. V0, V1, V2, and V3. Run the test again to make sure we didn't make any mistake. Still working fine, so that's good. And now we can start taking a look at implementing some of these methods. So do we want to name it translate or translation? I think I prefer translation matrix. And it's gonna take a vec3. If we take a look at this, the first translation matrix, it takes a vector 3. So basically you want to transform or translate your point by this vector or 3 coordinates. So if you have vector 10, 10, 10, 1, and you want to translate it 10 units in the x direction, you can have this 10, 0, 0. So I'm not sure exactly. Maybe I can just pass the 3 coordinates for now, so we don't have to introduce a vector 3 type. And we can construct this matrix simply by having 1 x. The second row is gonna be y, third row it's gonna be Z, and the last row is just a 1. And we can add a simple test for this as well. Translation. We can create the same example that they have in here. First, declare a vector. It's gonna be 10, 10, 10, 10, 1. And let m is equal to mat4 translate. I want to translate ten units on the x direction. So 10 for x and then 0 for the rest. And if we apply the transformation by multiplying, basically, if we do m times v, we should get a new vector 4, which should be the same vector but with the x coordinate added 10. So 20, 10, 10, 1, basically. Let's see if this test passes. We name this translation. Expected type. I missed the new here. And the test passes. Good. So we got ourselves a translation transformation. Let's see what do we have next. Next, they talk about the identity matrix. I have changed my mind. I'm gonna change this to translate, add a new one, scale. And also change the test. Translation. Right, should be still passing. The next one are scaling matrices, which is very simple as well, but instead of putting the coordinates in the last column to translate by that amount, we specify them on the diagonal. So we pass in three coordinates as well, and we just place them on the diagonal. So the actual implementation is pretty easy. We replace this 1 by x. This goes back to being a 1. This is the y. This becomes a 1 again. And set. Set. 1. Like so. We can add a simple test. Test. Scaling. Do they provide an example? Here they create a scaling matrix of 2 to 2. And they don't provide a vector. but it should be simple enough. So let the, I don't know, like 1, 2, 3. 1, 2, 3, 4, 1. I make it homogeneous. The transformation is gonna be scale 2 to 2. We expect that if we apply this transformation, m times 3, we should get back a vec4, which should scale uniformly by 2 on all directions. So 1 should become 2, 2 should become 4, and 3 should become 6. And the one on W stays the same. Let's see. This test passes. Left is 3, 5, 7. Really? So let me see, did I make any mistake? X, Y, Z. Do I have the expectation wrong? So I run Python. So 1 times 2 plus 2 times 0 plus 2 times 0. 3 plus 1 times 0. This is This is 2, which is okay. We failed on the scaling test, right? Yes, line 90. Scale X, Y, Z. X. This shouldn't be a 1, it should be a 0. Right? Yeah, we just have a 1 on the last column. So we got a bug with the test. It should be 0, and this should be 0. Let's see if now we pass. And the test passes now. So yeah, we had a bug in our implementation. Good that we have the unit test. Next comes the most complicated one, probably rotation matrices. Yeah, these are quite complicated. I'll skip the details here. It is not important to know their exact layout for everyday use. For more information, please have a look to the matrices and quaternions FAQ. Probably available on your language as well. I'm gonna open this and this. The model view projection matrix. So basically the way they create a rotation is by providing the angle in degrees and a rotation axis. Is it shown somewhere here, the formula? Curve, rotation. What is a rotation matrix? What are Euler angles? How do I generate Euler angles? I want this one. How do I generate a rotation matrix for a selected axis and angle? The simplest way to generate this type of rotation is through the use of quaternion mathematics. The following code snippet does most of the work, phi being the rotation angle and UVW the rotation vector. So basically we have this formula. Gonna copy this. So we're gonna take an angle, angle in radians, it's a floating point, and axis, which is gonna be x, y, z, or f2. Could be a vector 3, but we don't have that type yet, so let's do it like this. Then let's add a reference taken from here. This angle in radians. I think we have cosine methods like this in Rust, but our sine is angle in radians dot sine. And now we can proceed to create the matrix itself. First row is going to be arcos plus axis dot 0 times axis dot 0 times 1 minus arcos. Is this the second? The second row or the second column? Do they say something about that? What is the matrix? What is the order of the matrix? How do I represent? The simplest way of defining a matrix is to make the type def. Using two-dimensional arrays also incurs a CPU performance penalty in that C, blah blah blah. Matrix of 0 is the element 0, 0. the order is row first and column second. So yeah, I think that this should be columns. So basically this is the second row, first column. So W is, let's introduce constants also for this. Let u v w equals to axis. Excuse me. Now we can more closely copy the formula. So the second column is W times R sine plus V times U times 1 minus R cos. The third column is this thing. V times and we don't have the fourth column, so if we go back to Q38, don't forget to set the rest of the matrix to 0 except 1 at 3, 3. We are using 4x4 matrices. So this should be 0, 0, 0, and 1. Then we have the first column from the first row, so the second column, sorry. It's all of this. The floating point, then 0, 1, 0, 2 is this thing, and we have 0, 3, we don't, so then this should be 0. Oops. This should be 0. The third row, we already have the first column. We need the second one. The third, so that should be 2, 2, no, sorry, 1, 2, this one, and the last one is not specified, so 0, we only miss this one now. So 1, 0, 1, 1. One, 2. sorry, it should be 2, 1. This should be 2, 1 and 2, 2. 2, 1 and 2, 2. And 0, 0. Let's make sure that these are floating points. Now let's double check it, and I'm gonna move this around. So that should be the first row, then the second one, and the third one. So arc cost times U minus W times RC, V times RC, W RC. This one is incorrect. This one should be arc cost plus V times V times 1 minus arc cost. And then minus U RC V W minus V RC U RC. I think it's okay now. Formatted it like shit. Do they provide an example of this rotation? No, they just go to the model view and projection. So let's add a test for this. Let's see if we get the expected answer. Rotation, translations, okay. Let's have a vector for be just a vector looking to the right. So maybe 1, 0, 0, 1. Let's have the rotation M be rotation. And we want to rotate 90 degrees. So we have a vector to the right to rotate it 90 degrees so it looks up. 90 degrees, we need to transform it to radians, which is pi divided by 2. Do you have constant for pi? And the axis should be I think it should be 0, 0, 1, or maybe 0, 0, negative 1. Let's see what we get with 0, 0, 1. Then assert equals m times v is equal to a vector, which instead of looking to the right looks up in the y direction. It's in standard F32. They have pi divided by 2. Frac pi. Yeah, this looks like the one we need. F32 cons. Wow. Frac pi 2. We don't need to divide. Do you like that, compiler? Let's run it and see. Mat4, is it rotate? Maybe? Did I call it? Yeah, rotate. So we get almost the right result. If you look at the y coordinate, we managed to rotate. But in the x, we get a precision error. We get a precision error, and how do we deal with that? Do we have any helper? First, compare F32. Approx, there is a crate, looks like. F32 epsilon are available for the error margin. Yeah, we can do that. assert almost eq. Yeah. So we want to assert that actual minus expected but we don't have a way to subtract two vectors now. Shall we add it? I think we can add it. So we can implement impl sub all. Probably can add as well. Impl, where did I have it? Here. Impl sub for vector. Don't know what's the signature, but I can look for it. Can I derive it? No. They provide an example. And do I need to specify the type? I like to name this right-hand side. This should be Z, W, Z, W, W, Z, and W. Looks correct to me. So now we can subtract two vector force. And so we can do the actual result minus the expected. Absolute value is less than F32 epsilon. And this becomes now an assertion, not an assert egg equals. Let's give it a try. Method not found in that's right. If we could have a vector where all the three coordinates therefore coordinates are epsilon. But maybe we need to derive some trait in order to compare. Maybe we need the partial OR trait. We don't need. This is not gonna. Yeah, it complains that we need to implement partial OR. Can we implement it? Can we derive it? Partial egg and partial OR? Or do we need to manually implement it? Looks like we can, and even the test passed. But I'm afraid that if I switch the order, do we have a trait for absolute? Is there a trait defining this operation? We do, but it's on a separate crate, not on the standard library. So let's not do that. What happens if I move this to here? Will it fail? Yeah, probably it will. No. How can it be? How can it be? So the result, the actual is m times v, and the expected is spec for new 0, 1, 0, 1. So turns out that actual minus expected equals this, and expected minus actual is equal to that. Actual minus expected minus actual. These two are equal. Actual versus expected is, the first one is negative, a very small negative number, and the other one is positive, right? So the one that is negative, this one makes sense that is, or even probably this number is smaller than yeah, so if we had a bigger error on the magnitude, then the negative would still pass because we're comparing with the positive. I'm gonna do something which is implement apps for vector 4 the same way that apps is implemented for F32. So takes self and returns self, and then just x is equal to self.x.apps, and the same for the other coordinates. So y, z, w, y, z, w. Then we can call the apps like we were doing in the test before. Here we can replace all of these. Actual minus expected dot apps is less than I don't like to have this. What problem do we have now? Fine. Let it's fine. And we are passing the test. Cool. So this is a very simple rotation, but maybe let me see if I can come up with a new example. So if I have the same vector, but I rotate by pi, then instead of having y, we have a vector looking at the x direction. Y should be -1 on the x direction. need to duplicate the epsilon. Test this. So far, this case is also passing. I'm gonna make these methods, they are public. Why are you complaining that I'm not using them if I'm saying they are public? So line 60, I have translate and it's public. Why are you complaining? Is matrix 4 not a public type? It is. And on lib, we are using it. Oh, this is on main. Main translate line 60. This is weird. So math. It is complaining on the main function, but translate is defined here, so it doesn't make a lot of sense. Did I save all of this? Lib, save, main, save. Save, main was not saved. Now we don't get any warnings. Let me see the changes. And commit all of this. Git commit. Start. Add new module math with math for and back for types. Push this. Okay, so we have a basic implementation of rotations, so maybe we can start fiddling around with trying to rotate. So here we were setting the identity, right? What if instead of using the identity matrix, we do a rotate of 45 degrees, which should be const pi, let's make it pi divided by 4, and the axis should be the Z direction coming to me or into the screen. Wait, rotate didn't take a vector 4, it took a tuple with just the 3 coordinates, which makes more sense. So is it standard F32 consts? And if we run this, hopefully we should see the rectangle slightly rotated. Hopefully. And there we go. If I resize this to size, we can see that now we have the rectangle rotated 45 degrees. Let me look. So the green is on the left. So was the green on the right? If I undo this change, where do we have the green? Model. So the green is on the right hand side, and when we rotate it 45 degrees, it goes to the left, like so, right? Yes, yes. Very nice. So we have a rotating matrix now. Status, if apply a rotation to the rectangle using uniforms. I have to go, guys. Thank you all for watching. We will see each other next time, where we are gonna start animating with time. So today we did good progress. We got the basic matrix operations and vertex vector multiplication and so on. Next time we will try to animate this uniform, so we get a constant animation of a rotating rectangle. And also the next chapter that we will take a look at is about textures. So yeah, we will be able to see an image on the screen, hopefully, from an image. So that's all for today. See you next time. Bye.